Welcome to the first episode of our Ceramic Additive Manufacturing podcast, brought to you by 3D Ceram and Bosch Advanced Ceramics. I'm Sabine Tolachan from Bosch Advanced Ceramics, and I'll be your host for this session. Today, we are diving into the world of additive manufacturing of technical ceramics. We will explore how 3D printed ceramics perform under the extreme conditions of the aerospace industry. Joining me today are Charlie Clark and Eric Louradour from 3D Ceram. Please introduce yourself to our audience.
Hello, I'm Charlie and working as the technical sales manager for 3D Ceram for the past few years. I used to work on the machines as an R&D engineer, so I'm specialized in the technical aspects of the technology. Allow me to introduce 3D Ceram as well. 3D Ceram is a process provider with more than 20 years experience, with a history of previously printing parts before becoming a process provider. We've printed many different parts, from skull implants to semiconductor parts, going through the aerospace and the energy industries as well. We're working on new solutions to make bigger machines, bigger parts, and to use our expertise in artificial intelligence. And now I hand you over to my colleague Eric.
Hello, I'm Eric Louradour. I've been working at 3D Ceram for 4 years. Before that, I worked for 15 years in the field of ceramic membranes and catalysis. Initially at 3D Ceram, I was in charge of the process development. I worked to improve the manufacturing processes and on large printers. And as I am a ceramic engineer, I work on the development of new materials. And for a few months now, I'm in charge of the business development. So 3D Ceram has been working for over 10 years in the aerospace field by closely collaborating with organizations such as the French National Center for Space Studies and with major companies as Thales Alenia Space. So we are starting to have a good knowledge of this area.
Thank you, Eric and Charlie, and welcome to the podcast. I'm also very happy to welcome Johannes Noll and Ashu Sharma from Bosch Advanced Ceramics. Ashu, please tell our listeners a bit about yourself as well.
My name is Ashu Sharma, and I'm working as Chief Sales Officer for Bosch Advanced Ceramics since 2023. I'm specialized in technical sales and business development of ceramics and metals for 18 years. And let me also introduce briefly Bosch Advanced Ceramics. We are leading contract manufacturers specialized in additive manufacturing of ceramics. So we have a long history of manufacturing ceramics, and I'm proud to say that we are one of the top manufacturers when it comes to service providers for additive manufactured ceramics. From our headquarters in Germany, we deliver cutting-edge ceramic solutions to our customers around the world. Since 2016, we have focused on the additive manufacturing of technical ceramics, providing in-depth expertise at every stage of the process. Our expertise lie both in small and large series with the highest precision. Thanks a lot to our technical team for this, and a standard which has been made possible by the dedication and the skills of our technical team. One of my colleagues from this team is also present in the podcast today, and I would ask Johannes to introduce himself.
Hello, my name is Johannes Noll. I'm a development engineer here at BAC since 2021, and I'm working on the complete process chain. So starting from the customer's design, talking about possibilities, materials, doing the printing, cleaning, thermal process, and the quality control, of course, at the very end, and sending our happy customers their final ceramic parts at the very end.
Thank you and welcome too. So let's get started with the first question. To begin, could you, Charlie, give us a brief overview of how ceramic 3D printing actually works?
So there are several different technologies we can use to 3D print technical ceramics. It could be with VAT photopolymerization, it could be with extrusion-based technologies such as FFF, or it could be with jetting, so particle or binder jetting. And we can use these to print ceramics just as we do with polymers and with metals. If what we're looking for is precise and fully dense technical ceramics, then VAT photopolymerization is the best choice. And within this process, you can have different technologies available that also use different processes such as top-down or bottom-up. At 3D Ceram, we chose using the top-down option along with stereolithography, as it allows us to scale up and that allows us to print on bigger platforms. And also we have the gravity that plays with us as an asset rather than as an obstacle.
And Charlie, what kind of machines are needed to 3D print technical ceramics?
So for the space industry, we can print either very small parts, which is also very interesting for new space, or we can print much bigger ones, which is more for conventional space. Depending on the developments, you can begin with a small printer, such as the C101 Easy, and then scale up on a bigger printer. So you can start with a small part that you can then duplicate as part of a production system, or you can start with a section of a larger prototype that you can then validate before moving on to the larger printers. With this technology that we use, we are able to make a smooth transition from the smaller machines to the larger machines. And so this is part of what we've been working on for the C3601, for instance, as part of a collaboration with Thales.
And Ashu, could you give us an overview of the main advantages of 3D printed ceramics? What makes this technology special compared to traditional manufacturing?
This is a very good question, Sabine, and I would like to mention a few of benefits at this point. First of all, I would say one of the main advantages is the design freedom. Complex geometries and customization can be offered to the customers, and which allows the creation of intricate and complex geometries that would be difficult, or I would say impossible, to manufacture in the traditional methods. The second one is time to market in terms of faster development and validation. Additive manufacture allows for quicker iterations in design process, as it's a tool-free production method. It also saves a lot of time for the validation process, as material and process chain remains the same from the prototyping till the series. It's a very cost-effective for low volumes, as the setup costs are quite low, and unlikely conventional methods that often require expensive molds or tools, additive manufacturing has lower initial costs, making it more economical for small production runs, and it is a semi-automated production process. Integration of functions. So additive manufacturing allows for the integration of multiple functions into a single part, being it some hidden channels or being it some hinges which cannot be produced conventionally. And of course, it's a very precise production method, and the target is to produce the parts without going for any hard machining process. So, and also the tighter tolerances are possible.
All right. And Johannes, in your view, what are the most important factors during the production process to achieve the best results?
Yes, so we heard in Charlie's introduction that the technology is quite complicated. And also the technology from machine to machine, slurry system to paste system can be very different. So I think, or in my opinion, the key to having a successful part is matching the need from the customer to the best fitting technology, because each technology has its benefits and strength. And if you combine them with whatever is needed, high temperature tolerance or whatever, then you have a cost-effective part for the customer and its needs. Just as an example, if you want to print a disc, let's say with 200 millimeter diameter, you can't print that on a print bed that is 70 by 70 millimeter. So matching the right technology to the right part is one of the most important steps.
Now let's connect that to the aerospace industry. Eric, what new design opportunities does ceramic 3D printing offer for aerospace components?
Design freedom is probably the most well-known opportunity offered by 3D printing. In terms of design, you can imagine many things in the field of aerospace. For instance, lattice structure. Lattice structure is a little bit like the structure of the Eiffel Tower, with a lot of voids and many ceramic strands connected together. It's both very light and very strong. Or gyroid structure. It's also a very nice structure that you can be found in nature. And you can find also a lot of specific mathematical structures that are difficult to manufacture using traditional processes. The benefits of these structures is to lighten the parts while maintaining very good mechanical properties or improving their properties as permittivity, for instance, for antenna. You can generate also geometric gradients to optimize performances. You can imagine, finally, a lot of things. For space mirror, close back designs, reduce weight while improving part stiffness. Printing the component in a single piece eliminates assembly and machining use, avoiding potential weakening of the structure. And the last thing, maybe, we manufacture also smart parts of a new propulsion system for satellites with specific internal channels using for fuel delivery or gas evacuation. Complex channel geometry can influence gas flow dynamics, creating turbulence, or ensuring a more homogeneous flow distribution.
Thank you. And Johannes, what are your thoughts on that topic?
Yes, as we can hear from the explanation of Eric, lots of things are changing with AM. So the traditional approach of designing a part, then testing it is a little bit outdated. And I wanted to highlight, for example, topology optimization. So this is an approach of working basically backwards. You have your forces or the load of your part, and you let the simulation and the computer calculate the part you need. So you get your form after your function. Usually those parts are quite complex and tooling wouldn't make any sense, but the 3D printer doesn't care about the complexity. So that's a nice little approach that New Space is already implementing and that AM can benefit from. The second thing I would like to talk is that because the technologies usually work with a mixture of powder with binder, and during the debinding process, you burn out this binder. This means that the wall thicknesses that are realizable with the technology, they have a limit. That is actually for the space industry a huge benefit, because if you have a limit in the sense of wall sizes, you automatically have lightweight designs. So in that case, the aerospace industry is a happy customer of ceramic AM. And the last point I wanted to make is that the approach of taking apart an assembly group, for example, to manufacture it conventionally is needed with AM. The 3D printing process encourages you to print complex parts with lots of features already integrated. So if there are any engineers listening to this, look at your assembly groups, try to combine as lots of parts as possible. Usually you get a cost reduction just by having less parts that need assembly, for example.
Okay. Besides design freedom, Ashu, what are the manufacturing advantages of ceramic 3D printing that are especially useful in aerospace?
So some of these advantages have been already mentioned by Eric and Johannes. And I would say additionally, the main benefit or advantage of additive manufacturing is the flexibility of 3D printing. You can easily scale the production volume from small to large, and it even offers a lot of benefit in terms of design flexibility, and also brings all the features or the characteristics of ceramics with it. So if characteristics wise, there is not much difference noted in terms of the properties of ceramics. So the properties are still there, be it high temperature resistance or corrosion resistance, and the additional benefits are that the lightweight structures are possible. So in my opinion, it is a very useful benefit for the aerospace industry, because here every gram counts.
All right. And Charlie, what are your thoughts on that?
On from Ashu's comments, there's of course the flexibility that you have going from a smaller printer to a larger printer, but there's also the flexibility that you have in the same printing run. Using additive manufacturing, you can create parts that have different geometries and different sizes on the same printing run. And of course, the larger the machine, the more variations that you can then put onto that platform itself. Having this kind of flexibility, but also independence, where you can have a small production unit with a printer, a cleaning booth, some furnaces, allows you to have a local production unit, and it can also reduce logistic times. But that independence as well, of being able to keep your designs confidential and keep all of your own IP in-house, rather than having to share this with subcontractors.
Okay, thank you. Now let's move on to applications. Can you, Eric, share some specific examples where functional integration was only possible through additive manufacturing?
Yes, for a French company, we have produced zirconia parts with a specific lattice structure that they integrate into the satellite antennas. The lattice structure, along with the intrinsic properties of zirconia, optimize the propagation of waves. Another example is that we produce parts for satellite engines powered by plasma, which required internal channels only achievable through 3D printing. Ceramics is also necessary in this case due to its high chemical inertia and also plays the role of an electrical insulator. We have the same request with new structure or architecture, only achievable via 3D printing for heat shield optimization, for instance, to enhance thermal shock resistance and to lighten and make functional telescope components. My last example concerns radomes, where 3D printing is also interesting because it allows for structuring the inside of the parts to improve their mechanical properties, but also to give them new functions.
Okay, and Johannes, what are your thoughts on that?
Yes, so we also have some very interesting examples. I already talked a little bit about combining assembly groups. So with the conventional manufacturing, a lot of the steps are screwing things together, gluing them onto each other or whatever. So by just adding functionality, by adding parts to the core function, we see a lot of very AM adapted designs from customers that save a lot of time and energy at the end. But just think about, for example, individual markings or labelings. If there is a laser marking process at the end of your ceramic process, that's not needed with AM, because each part can be different. They can be numbered, they can be labeled. The point that Charlie was making with rethinking production and supply chains is also very interesting. AM is fast, flexible, can have mixed print shops. The way traditional, conventional manufacturing usually has very long lead times, that's just not the case for AM, where we are considerably faster. Another added function is, of course, internal channels, as you know from other AM processes. We've had the ceramic as a carrier plate, where a customer is printing electrical circuits onto the ceramics. We had some very good results with printing threads. So the way that conventional manufacturing is adding threads is hard machining them into the part, which usually leads to cracks or defects in the parts. With ceramic AM, you can just print those parts into the design.
Okay, and Charlie, the next question is for you. What is your advice for designers? How do they need to think differently when developing parts for 3D printed ceramics compared to traditional ceramics?
I think Johannes touched upon this subject a bit earlier. The main takeaway is that you have to really break the barriers of how designing for conventional parts has now changed. So rather than looking at how you can take a simple block, for instance, and use subtractive manufacturing to make it into a part that you can then use. It would be more to design the most optimal part possible and then to make that part 3D printable. So starting from 100% efficiency and performance and then reducing it as little as possible while making it sure that it's a part that's printable and that's also going to survive the rest of the process with the cleaning and the firing. So it's really a paradigm shift compared to what you had to go through before and how you had to design parts for conventional manufacturing, because now 3D printing has its own design rules that are far fewer than that and opens up a lot more freedom and choice and imagination when designing the parts.
And Johannes, what are your recommendations for designers?
Yes, so in the very beginning, I talked about rethinking a little bit how we approach the design for AM. We get a lot of questions of, hey, do you have a design guide? So I would like to go over some numbers that are just important. Additive means step-by-step layer addition to produce a part. Those layers can differ in size. So you can have layer steps down to 10 microns, or you can have very large layer steps up to 100 microns. It's all about matching the right machine, the right parameters to what the part needs, what the customer needs. If the part demands support structures, we have systems that have contactless support. So everyone who has an FDM or an SLA printer at home knows those support structures that have little pins connected to the parts. Contactless support means those pins aren't needed, which is a nice way of skipping that green machining step and having a supported part that is going right into the furnace. We're talking internal structures. So Eric was talking about lattices, any infrastructures. That's something that's possible with quite every technology available. If we're talking wall thickness, so what's doable there, you're safe up to 5 millimeters. If you're going above that, maybe we need to have a look at your design. If you have tolerances on your drawing, what we can guarantee on the very first print shop is plus minus 0.5% of the nominal dimension. That's down to about plus minus 40 to 50 microns. If you have tolerances that are below that, usually we need an iteration cycle just to find out if we can hit that.
And Johannes, let's now have a closer look at the material. What types of ceramic materials do you offer for aerospace applications, and what are the performance benefits of these materials?
Yes. So the material question is hard to answer because there are lots and lots of materials out there. Here at BAC, we're doing about 90% of our volume with oxides, specifically talking about alumina and zirconia. Alumina, if you compare it to zirconia, alumina has a lower fracture toughness and a lower flexural strength, but higher hardness and a better wear resistance than zirconia. If you need an thermal isolation, you would go with zirconia because alumina has a higher thermal conductivity. If cost is a factor, you would probably choose alumina because it's a little bit cheaper. If you're looking for good chemical resistance, you would choose alumina. If you're looking for electrical insulation, you would probably use alumina. It's all dependent on the need of the part and the customer and what functionality it needs. So that's very individually has to be assessed, but that's what we're here for. We talk daily with our customers about their applications and their needs. But I'm very much looking forward to hearing from 3D Ceram what they have been working on lately.
In our side, we use also a lot of standard oxides, alumina, zirconia, but we are also working to meet specific requests such as cordierite, which has a low thermal expansion coefficient, or fused silica, which is transparent at certain wavelengths. An important topic that we are also working on, nitrates. They are more complicated to print because of their UV absorption, but we have made a lot of progress on this subject, and we are now able to produce large parts. Nitride addresses many challenges in space. In space, materials need to be strong, light, and able to handle extreme conditions like heat, cold, and radiation. Two materials that are very useful for this are silicon nitrates and aluminum nitrates. Why silicon nitrates? Because it's very strong, even at high temperatures. It's lightweight, which is important for rockets and satellites. It resists wear and oxidation, so it lasts a long time. And finally, it can handle sudden temperature changes without breaking. That's why it's used in things like engine parts, thermal shields, and satellite structure. For aluminum nitride, it's different. It has an excellent thermal conductivity, meaning it can carry heat away quickly, and it's also an electrical insulator, which is great for electronics. It handles thermal shock well, which is very important in space, where temperature change very fast. And it's often used in electronic system, heat sinks, and radio frequency component on satellites. So silicon nitrates and aluminum nitrates are perfect for space because they are strong, light, and reliable. They help make space system safer and more efficient.
Okay, and then now, Charlie, how do you support your customers, not just with materials, but throughout the entire process of developing their application?
So considering the history of 3D Ceramic of producing parts, it's very easy to put ourselves in the shoes of the customers that wish to develop their own products. So for us, we're looking at the specifications, we're looking at the feasibility of what they want to produce, not only the design, but is it something they're going to be able to take to a large scale? Are they going to be able to manufacture the quantities they want to, but also at the tolerances and the quality that they need to as well. So in order to do that, we speak with our engineers here, we work on the feasibility, we look at the printing information, we try to provide as much information to them as possible so that they can then make the necessary calculations to work out which is the best solution for them. We also look at the process constraints as well to ensure that not only are they able to print the parts, but can they go through the entire process from A to Z and be able to incorporate that into their own production system as well.
Okay, and Ashu, what can you share with us about supporting your customers?
So as I mentioned before, that we are the right partner when it comes to the series production. So we support our customers from the consulting till the series parts. So we start with as I mentioned, we assess the need of the customer, what is their main pain, because if the product would be very simple, they would like to manufacture it in the conventional methods, and they are looking for the right partner who can manufacture or meet their demand for the series parts. And we have the ability to scale up the parts in the higher volumes. So after assessing the needs of the customer, we also offer them sort of design support, because the parts they need to be designed for additive manufacturing, which means some small iterations might be needed, as Johannes mentioned, maybe some wall thickness or some sort of structure is needed, etc. And thereafter, we offer our customers the prototypes and also are able to do iterations quite fast. And it's not only that, it's also ongoing support and strong communication, interaction with the customer, because it needs a dedicated account management as well. And at the end, the customer wants to produce their products and bring them to the market, and it needs a lot of, I would say, dedication and also communication with each other to make a successful product. And beyond that, we also support our customers for being innovative and also offer some sort of R&D collaboration for long-term partnership and for the new projects.
Thank you. And now let's talk about performance in space. Space is a tough environment. So, Johannes, how do 3D printed ceramic parts perform under such conditions?
Quality, quality, quality. So if you bring parts into space, of course, they have to be perfect. 3D Ceram has some amazing examples, like with their mirror holder of very big parts. What we've been doing is also some rather small hidden champions, I would call them. They are the ceramic parts are sometimes quite well hidden and performing in environments where metals and plastics just couldn't stack up. Because we are a service provider and we're producing parts for customers, and confidentiality is very important to us. We usually are very proud of our parts, but we can't show them. So the example I would like to talk about is something that we've done for a customer. It is a small plug adapter for a rocket propulsion system. And it basically combines two main functions. It is made out of zirconia, and as I said before, it has the great property of isolating temperature very well. And the second thing that was important for that part is that there's a very smooth running thread already printed in the part. And because it is printed, it has very little risk of cracks or any defects in the parts. So with those two properties combined, that rather small part is contributing quite a big thing to that propulsion system.
Eric, what can you share with us about the performance of ceramics in space?
Thanks to their properties, ceramics are inert materials well suited to the space environment. NASA, with one of our printers, is currently studying and quantifying their performance under the MISSI project. One of our customers also has over 200 3D printed ceramic parts currently in space.
And Eric, how do these parts perform when it comes to electrical insulation, thermal stability, radiation, or thermal cycling?
Ceramics are valuable in space because they are lightweight, they resist heat above 1000 degrees C without any problem. Corrosion, radiation, they are very hard and wear resistant. Ceramics are also good electrical insulators. So ceramics tick a lot of boxes to meet the needs of space. These properties make ceramic essential for components like thermal shield, sensor, engine parts, and electronic system.
And Johannes, what are your experiences when it comes to these properties?
Yeah, I absolutely agree with Eric. And maybe I can add that if you compare conventional ceramics, so if we're talking pressing, if we're talking injection molding, then AM is always in the business of being compared to those conventional and very well established and known production technologies. And in the experience we've had over the last couple of years, AM ceramics, if it comes to mechanical properties, chemical properties, electrical properties, matches up conventional or conventional manufactured ceramics.
And Johannes, how resistant are these parts when it comes to mechanical stress like vibration and shock?
Yes, so in that case, it's each part is different. So it's very much depending on what application we're talking about, what part we're talking about, and what function is needed. What we are giving our customers is the possibility to do simulations themselves. So when it comes to mechanical stress, all the software everyone knows is very capable of performing tests to see if the ceramics can handle that stress. So the performance I was already talking about is very comparable to conventional methods. So simulation is one way of making sure that your design is working.
Eric, what can you share with us about mechanical
We have some result about that, as we already have partners who did certified 3D printed ceramic parts that are actually in space right now. So that means that we have the proof it works.
And Eric, let's now look at quality control. How is quality controlled in ceramic 3D printing to make sure parts meet the required standards?
The same control as for the conventional ceramics, more specific to aerospace controls, actually done by our customers. But go further.
Johannes, what can you say about that?
Yeah, I agree. So it's the same as with conventional ceramics. As Bosch, we can, of course, offer to do lots of testing in-house. So if a customer wants a CT scan of the first couple of parts they get, we can make that possible. We have RAM imaging with sputtering available, EDX structural analysis. If you're interested in the density of our green parts, we have gas pycnometers. If you want the density, which is very common, of your final sintered parts, we offer Archimedes density measurements, visual inspection. The list goes on and on.
Okay. And now looking at the market, Charlie, what kind of applications or requests do you get most often from customers in the aerospace field?
So as Eric has mentioned before, we've worked on thruster systems, so different propulsion systems, in new space as well as old space, but working on different systems, different propulsion systems that are kind of proprietary to individual customers. We've worked on the development of next generation launchers, so that's to make them reusable, as currently they're only single use. We've worked on heat shields as well that are normally made by conventional methods, but looking at how we can make them more efficient with additive manufacturing. We've worked a lot on the past in structural parts of telescopes, working on mirrors as well, which we've shown we can print from small scale to large scale on the machines. And of course, because we have the different materials available, we can work on thermal isolators as well as thermal exchangers. And I'd say the most recent kind of topic of discussion has been the use of regolith material, with the question of can we print on in space itself.
Ashu, what can you share about that?
Yes, I agree totally with Charlie on this. We also get similar kind of applications, inquiries from our customers. And the main focus of these inquiries is, of course, lightweight and also design complexity.
Okay, and now to wrap up, Eric, what are some of the most exciting developments or innovations you expect to see in the near future?
Okay, the most exciting developments or innovations. Not so easy to imagine. The long journey in space will require new capabilities from space transport and communication systems. And the establishments of live camps on the moon and then on Mars will necessitate being autonomous. It will be necessary to generate electricity, water, and manufacture object resistance to environment directly on site. So 3D ceramic technology has a significant role to play in the space adventure. The same goes for the development of new, more efficient telescopes that will allow us to continue searching for the origin of the world, for instance.
Okay, and Ashu, what do you expect to see in the near future?
So in the near future, I see more and more applications coming in terms of new space, which means in the monitoring of different fields. That is one thing I see upcoming very fast. But nevertheless, AM is growing very fast, and our experts are working on pushing boundaries of the technology on the daily basis. And in my opinion, also high temperature resistance products for hypersonic and also space applications would be the next challenges that we would have to deal with. And thanks to the technology and also the material developments, I am very confident that we shall be able to meet the requirements of the next generation products.
Thank you. That was both inspiring and exciting, and a great way to wrap up our discussion on ceramic 3D printing in aerospace. It's clearly a field full of potential for innovation in the commercial space industry. A big thank you to our guests from 3D Ceram and Bosch Advanced Ceramics for sharing their insights, and thank you for tuning in. If you would like to learn more or connect with our experts, you will find links and resources in the show notes. Don't forget to follow us on social media for updates on future episodes, and feel free to share this podcast with colleagues who might be interested in advanced materials for space applications. Thank you, and until next time.